Swayam Prabha. Digital India. Educated India.
Okay, so we will talk about digital signature standard, which is basically based on the we use the SA secured hash algorithm to reduce the plain text in a 160 bit. So, as you know, hash function can take any size plain text m. So, it can take any size plain text m to a fixed size digest. In general, it is L bit. Now, for SA1, if we use SA1, so this is basically give us 160 bit. So, this is H of m. This we denote by small m. Okay, so it is basically use the in digital. So, DAS basically use what is called SA and DSA, digital signature algorithm. So, we will define what is digital signature algorithm. So, this is basically NIST published this in this DAS in 1991. So, this is the first version was proposed and it was revised again in 1993. So, this is a standard made in 1993 for a digital signature, and this is used, as I said, secured hash algorithm for the digest purpose for the compression, because our message could be long enough. So, we have to make it small, and then it is used the digital signature algorithm, which we will discuss, and there are some modification on this extended version of this standard like this. Okay, so, but here we discuss the DSS algorithm, which is based on the DSS, which is based on the DSA algorithm. So, we will just look at this. This has few step like key generation step, which is called the DSA parameter. So, let us just talk about the how we can choose the parameter for DSS. So, we are talking about digital signature algorithm. This is basically make use of the Elgamal signature scheme, where but the message we digest, because message we are taking to be any message, long message m, and but it has to be digest to the fixed length 160 bit. Okay, so, we have to use the SA1. So, this is the digital signature algorithm. This is also DSA. Okay. So, DSA use the following parameter. DSA uses, this is the key generation step. This parameter is standard parameter. That is why for standard we have to make this. So, this parameter are basically we choose a p. Let p be a prime but p is coming from such that 2 to the power L minus 1 less than p less than 2 to the power L, where L is basically L is the number of bit. So, L is basically lies between L, where L is a multiple of 64, is a multiple of 64 and L is coming from 512 less than equal to L less than equal to So, P is a large prime, P is a L bit prime, and L is a multiple of 64 and L is taken from this. Now, we choose another prime Q, Q is another prime, and for Q also we have the range coming from 2 to the power 159 less than Q less than 2 to the power 160. So, Q is 2 to the power 159 bit and such that Q should divides P minus 1, such that Q should divides P minus 1. Q must divides P minus 1. So, we choose another prime such that this Q should divides P minus 1. Now, we choose a G, we compute G which is basically so we compute G which is basically coming from h to the power P minus 1 by Q, because Q divides Q divides P minus 1. So, that is an integer. So, and where h is an integer in this range. So, we choose h to be less than P minus 1 to P minus 1, and so let us write this. So, G is we calculating h to the power P minus 1 by Q. That is why we need Q must divides P minus 1. Okay. So, this mod P. Okay. So, now we choose a random integer, So, this is all key generation, these are all parameters, standard parameter for this standard random integer x such that 0 less than x less than q. Okay. X will be the private key for the individual and we compute y will be the public key for each individual. We compute y is equal to g to the power x mod p. So, g we know, so we can compute g to the power x mod p, and this y will be the public parameter of the individual and x will be the private parameter of the individual. Okay. So, now 6, let us just erase this. Okay. So, this is 5 and then 6 basically 6 is we randomly choose a k from random integer k from 0 to q. Okay. And this k is required for each signature, because k is, if you recall the Elgamal crypto system, the for encryption we need to choose a k by the signer or encryptor. Okay. So, now and so this is the parameter specification. So, we have to choose a prime p which is basically L bit, and L has to be range from 512 to this any value. Okay, and but L must be multiple of 64. So, we have to choose a prime p and we have to choose another prime q which is basically 159 bits, but it must q must divides p minus 1 because we have to calculate this. So, we compute g for a h less than q minus 1 mod p, then we choose a random integer x, x is the basically x is the private key of an individual and y is the public key of an individual, and the remaining we can make it public. So, public keys basically are public key is basically P, Q and G. So, these are the keys can be shared by the group of user, can be shared by the group of users. Group of user means, because this is a signature standard, so there are many parties are involved, but one party is one individual is signing, but this checking verification can be done by any party. So, this is there is a group of users Alice, Bob, Rob, Polas, Bimal. So, among these, so these are all the parameters are publicly known to the all the users. So, these are the part of the public parameter. Okay. But for individual, for an individual user who is signing, an individual for an individual user, for a signer, who is signing, basically signing user, X is the private key or the secret key, this X. So, this X is the private key of or the secret key of the signer, and this Y is the public key. Okay. So, this K is chosen by the signer at the time of signature, because K is another parameter which is sort of nonce or time stamp for that particular signature. This is basically Elgamal signature. So, this is the parameter set. Now, let us talk about the signature. Now, using this parameter, suppose Alice wants to send a message. So, this is the standard parameter we will use for this digital signature standard. Okay. So, now how to sign a message now using this parameter setup. So, the message could be any length. So, but we have to make it we have to compress it. So, this is the signature part. So, this is doing by the signer. Okay. And the verification can be done by any other users which belongs to that group. Okay, let M be the message, or plain text, and M is any arbitrary bit. It is a big message. Okay. So, now we will make use of hash function, especially for this standard we have to use the secure hash algorithm or SA to. So, if we use SA on this, we will get M. So, this is basically 60 bit. So, this is small m. So, this capital M, we use the SA hash function and we make a 160 bit digest. Okay. So, this the signer has to apply H on this and get this. Okay. Then signer will compute R and S, that is the signature part. This is basically the Elgamal signature. So, how we can compute R? So, suppose Alice is signing and send it to public channel Bob, Rob. So, this is the group of users Pimal, Polas. Okay. So, Alice is computing what? G to the power k, because k as is choosing, G is public, G to the power k mod P mod Q. Okay. And S is basically k inverse M plus XR mod Q, and Alice is sending this RS to the verifier. So, this is signer signer and this verifier. So, the signer is sending this RS to the verifier. Okay, so, this is the signature part, but here we are using the small m because this is after applying the SA. Okay, now, how to verify it? How the verifier can verify it? So, that part we have to talk about. So, let us just write this here. R is basically g to the power k mod p mod q, S is basically k inverse m plus xr mod q. So, let us have this. In the verification step we need this. Okay, so, now how to verify it? So, verifier is receiving R and S and verifier is having all the public parameter. So, using that verifier has to verify this. So, this is the verification step. Okay, so, verifier knows this, knowing P, Q, G, these are all public parameter, and the Alice or the signer public key Y, and verifier also knows M. M is the message. So, message is also has to send. So, this Alice is sending, Alice is the signer, M along with the R and S, and Bob is already having this public parameter like P, Q, G, Y, yeah. So, R as and S are name Bob is getting now. So, now Bob has to verify, this is Bob, sorry, Bob has to verify this message is signed by the Alice. So, the verification is done by this. So, R and S. So, Bob will compute this T, which is basically M S inverse mod Q. So, Bob can compute because M is basically H of capital M. So, hash function is public. So, Bob can easily get this, and S is coming from Alice signature. So, Bob can get the S inverse by the extended Euclidean algorithm and can get this. Okay. T Bob can calculate. Q also R S inverse mod Q. This is also can be computed, and V is basically g to the power t, this t is here, y to the power u mod p mod q. Okay. And the verification is like this, and verify whether this V is R or not. If V is R, then the signature is valid. If V is R, then the signature is valid. We have to check this, then the signature is valid. So, this we have to check whether V by computing this is giving us R or not. So, R is that. So, let us write V over here. So, V is basically okay, let us just write here T is equal to M S inverse mod Q and U is equal to R S inverse mod Q, and V is basically g to the power t y to the power u mod p mod q. Okay. So, now we are checking whether V is equal to R naught. So, why this will give V is equal to R? Let us just check this. Okay. So, S is this. So, if we just take S inverse, so S is this. So, S inverse mod Q, S inverse mod Q is same as, so this is K inverse, this inverse mod Q. So, k into m plus xr inverse mod q. Okay. Now, this implies S inverse m plus xr if we multiply, this will give us k mod q, this will give us k mod q. Okay. So, we are multiplying just m plus xr. So, it will cancel out, it will give us k mod q, sorry. So, V is basically g to the power t y to the power u mod p and then mod q. So, this is basically g to the power t is basically m s inverse, g to the power m s inverse mod q, and because t is m is s inverse mod q, y to the power u is basically r s inverse mod q, then mod p mod q. Just simplifying this, very simple. Now, y we know, y is basically what? Y is basically g to the power so this is g to the power x basically. So, we can just write g to the power x. So, this will be g to the power m s inverse m q mod q into y is g to the power x. So, g to the power x r s inverse mod q mod p mod q. Okay. So, this will basically give us g to the power m s inverse we take common m plus x r s inverse mod p mod q, then mod p and whole mod q, and this is equal to what? This is equal to, we know this is S inverse this mod p is equal to k. So, this is basically g to the power k mod q, then mod p mod q. Okay. So, this is basically r g to the power k mod p. So, this is basically r. So, this is valid. So, this is basically r. So, if we get this r, then basically we are getting this if you get this r back, then that is the verification, that is having the verification. Okay. So, this is the digital signature standard. So, let us come to the slide please. So, this is the parameter we are choosing. This is the public user, individual user public key Alice, this is the user secret key, and this is the k, which is the random number chosen by the signer, and this is the signature. Here this is our small m, h of m, and this is the verification. If v is equal to this, then we are done. Okay. So, this is just what we have discussed. This is the, now let us come to the picture. So, this is the pictorial view of the signing and verification. So, F1 is basically f of, so we have these inputs are basically P, Q, G, and we have K. We are applying SA here to make it small m, then we are applying this F1, F1, F2 is defined like this. So, it is basically the graphical notation of this. So, it is basically giving us R and S. So, once we got R and S, Alice is sending to Bob. Now, upon receiving this R and S, how Bob is verifying? Bob is having the message. Also, you have to send the message. Then Bob is calculating this and getting by calculating this V is equal to R or not, checking and verifying. Okay. So, let us take an example how it is working. A quick example. Okay, so suppose we choose q is equal to 101 and p is equal to 1, 2, 4, 8, 5, 6, 3. Okay, then we can easily check p minus 1 mod q is basically 0. So that means q divides p minus 1, that we can verify. Now we choose g, we choose h to the h is equal to 2. So p minus 1 by q mod p, which is, if we calculate, 588,634. Okay. Then you compute. So we can just check this, g to the power q mod p is basically 1. Now suppose Alice has to send a message, say 23. So now y is basically, no, this 23 is not the message. 23 is the Alice public key, Alice secret key. This is the private key of the signer. And then we need to compute y. Y is basically g to the power x mod p, which is basically 702644. Okay. Now suppose we have a big message and we convert it and we got m is equal to 53, small m, and we choose k is equal to 42. Then we have to compute r and s. So r is basically what? R is g to the power k mod p, then mod q. If you compute this, we will be getting 52. And then s is basically k inverse m plus xr mod q will be getting 61. So you have to calculate this 61. So these two will be sending to the verifier 52. So r and s 52 and 61. So upon receiving 52 and 61, the verifier will be verifying this by calculating just t is equal to m s inverse mod q, which is basically 82, and u r s inverse mod q, which is basically 29, and check v, compute v, g to the power t, it should be r, y to the power u mod p mod q. So this is 52, which is same as this r. So the verification is done. Okay. So the verification is done. So this is the digital signature, and for this standard purpose we need to use those parameter as specified by the designer and as accepted by NIST as a standard. Thank you.